We begin this section with a discussion of a new operation on vectors, and then we'll talk about how that operation is useful. The operation is called dot product, and we make the calculation like this. Suppose vector u in component form is 5, 2, and v in component form is 3, 4. The dot product of u and v is found by multiplying items that are in corresponding positions and adding those products. So it's 5 times 3 plus 2 times 4. And collecting here, we find the dot product of u and v to be 23. Here's one of the nuances involved with finding the angle between vectors. Suppose the vectors are 4, 6, and 3, negative 2. And we want to use our formula here to find the angle between them, and we go about the business of making the calculation. Let's see, the dot product of u and v in this case would be 4 times 3 plus 6 times negative 2. And in the denominator, it's the, let's see, for the magnitude of u, it's the square root of 4 squared plus 6 squared. And for the magnitude of v, it's the square root of 3 squared and negative 2 squared. All right, and then, let's see, in the numerator, we have 12, and 6 times negative 2, that's negative 12. 12 with negative 12, oh, that's 0. And in the denominator, we have the square root of 52 and the square root of 13 for the factors. But it really doesn't make too much difference in the denominator because the numerator became 0. And when the numerator of a fraction is 0, the whole fraction becomes 0. And if the cosine of theta is 0, then the inverse cosine of 0, the inverse cosine of 0 turns out to be 90 degrees. That is, the angle whose cosine is 0 is a 90-degree angle. So the two vectors then are relatively perpendicular. They're perpendicular to one another. Now, if we actually position these two vectors at the origin of our coordinate plane, we can kind of see it pretty easily. We have a situation where, let's see, we have u is 4, 6. That's about right here. And v is 3, negative 2. About right here. And that is a 90-degree angle. Now, if they're positioned in other places on the coordinate plane, they're still relatively perpendicular. That is, if this vector is up here and this one is, over here, then by extending them in both directions, we can imagine that they are perpendicular. Now, this relative perpendicularity idea has a special name in trigonometry. It's called orthogonal. The two vectors are said to be orthogonal if the angle between them is 90 degrees. Now, let's review the idea. We start out with this formula for calculating the angle between the two vectors, but if we find that the dot product is 0, that's just the numerator up there, then if the numerator turns out to be 0, then the whole fraction is 0, and the cosine of theta then is 0. Theta then is 90 degrees, and the two vectors are said to be orthogonal. When we studied vectors in the xy plane, and we came to the point where we were talking about the angle between vectors, we quickly determined that if the angle between the vectors is 90 degrees, then the cosine of 90 degrees is 0, and therefore that fraction on the right side of the calculation is 0. And for that fraction to become 0, its numerator has to become 0. And so the dot product is equal to 0. So we said, let's kind of work backwards or think backwards from that notion. If the dot product of a couple of vectors is 0, then that fraction will be 0, and the angle will be 90 degrees. Now, a 90-degree angle between vectors caused us to classify those vectors as orthogonal. Orthogonal vectors have an angle between them which is a right angle. All right, so that's the idea. Then we quickly came to another determination having to do with parallel vectors. Now, they can be parallel either facing in the same direction or in opposite directions, but if they're parallel, then that fraction on the right side is -1, and we made a determination and a calculation that the two vectors turn out to be scalar multiples of one another in that circumstance. So, if we have scalar multiples, if we have vectors that are scalar multiples, it implies that those vectors are parallel. And if we have a dot product that's 0, then the two vectors are orthogonal. Now, we can make the same discoveries and the same kinds of determinations in 3 space. That is, if U has this component form and V has this component form. We'd like to know if U and V are orthogonal, parallel, or neither. And we understand that a dot product of 0 implies orthogonal vectors, and if the vectors are scalar multiples of one another, then they are parallel with one another. Well, we can quickly dispense with the idea of scalar multiplicity by looking at the components within the two vectors. Now, if this rascal is a scalar multiple of that one, then it means that we need to be able to multiply some number out here times each of these, same number, to get those entries. So for the first entries, if we used a 6 out here, 6 times 1 would be 6. However, 6 times 5 would not give -3. And so we don't have this scalar multiple idea going on between the vectors. Now, dot product we can determine very quickly as well. The dot product for U and V would be, let's see, U dot V would be, and now we're just multiplying corresponding entries, so it would be 6 times 1 from above plus, let's see, -3 times 5 plus, and then 3 times 3. So 6 minus 15 plus 9. Collecting, we find this value to be 0. If the dot product is 0, we conclude that the vectors are indeed orthogonal.